Welcome to Einstein's Mechanics. In this episode, we are going to talk about the integral test. So this test is going to help us determine the convergence and the divergence of a function. So just as we did for the P series test, we are also going to use a test again called the integral test. It's very simple. So for any series given to us, say for a series in the form an, we are going to represent the series given an in the form of what? A function of what? X. Are we okay? We are going to represent the function in terms of x, and we use integral to solve. But there are conditions for the integral test. Anytime you represent a function, so this is going to be this way. We have a function given from n is equal to 1 to infinity of, say, a function a of n. We are going to compare this function to the integral from 1 to infinity of the function of f of x dx, where f of x is equal to a of n. That means the function given is what we are going to integrate. Are you okay? So before we can use the integral test on any function to test for the convergence or divergence of a series, the function must have three things we are looking for. The function should be what we call continuous. The function should be continuous. The function should be positive. And the function should be decreasing. So we will look out for these three things in every function before we can conclude that the integral test can be used for that particular series. Are you okay? So what you have to note is that if the integral test diverges, so if I solve for the integral test and it diverges, or I got a diverging series from the integral test, therefore the function or the series itself is going to what? Diverge. So if integral is diverging, the function or the series is also diverging, and vice versa. So a converging integral means what? A converging series. Very simple. So this is what we are going to use. So anytime we solve for a function such that we have a finite or a definite value, then we are saying convergence is what taking place. But anytime our series or our integration goes towards infinity or infinite, then we are going to say it is going to what? Diverge, just as for any series test. Very good. All right, so there are some keynotes we should pay attention to, apart from the fact that we are going to test the equation or the function by knowing if it is continuous, positive, or decreasing. There are some key terms we should pay attention. Now, the number one is saying that the integral test tells the convergence or divergence of a series, but not necessarily give the sum of the series. You understand? So, for example, I know that I'm summing a series from 1 to an infinite value of a function a of n. So, assuming this series is a GP, where we know that sum to infinity is given by this 1 minus r. this formula is going to give you the total sum from 1 to infinity, summing all the series. But we also have an idea that integration, when we plot a graph for integration like this, we want the area under the graph from a point 1, let's say, to infinity over here. So integration means we are going to add the small areas around or below the graph to get the entire area below it. But when we come to the test this way, we are saying if we have a function a of n where we can sum it from 1 to infinity with this formula, if it is GP, the integral test from 1 to infinity of that same function where we are representing it by f of x is not definitely going to give us the sum, but it will tell us if it converges or diverges, because this will either give a definite value or it will converge or diverge at infinity. Are we okay? So the integration is just going to help us determine convergence and divergence, but not necessarily the entire summation. So the value you get for the integration is not necessarily the summation of the entire series. That's one. Are we okay? So the second point is that when we are using the integral test, convergence and divergence will not be affected irrespective of the continuous interval we choose. Now, check the integration of 1 to infinity of the function a of n, where we are saying it is going to be integral from 1 to infinity of a function of what? X dx. Are we good? We are saying the continuity, are we good, will not affect the convergence. That means there is a case I can solve where my lower limit of the integral is going to start from 3, like this. Are we okay? It is going to start from 3 to infinity. There is a case you can start from, say, 5 to infinity. This 5 to infinity, just as we know from rule 1 that it is not going to give us the direct sum of the series, but from this 5 to infinity is always going to give us a value showing the divergence or convergence of the series. So please pay attention. We'll solve example. It is not always that, although the series is saying from 1 to infinity, that we are going to use the integral test also from 1 to infinity. Sometimes the series will say 1 to infinity, but the integral test can start from 5 to infinity. And that does not mean it is going to give you a value which is equal to the sum. But wherever we start, the lower limit to infinity, it is going to tell us if it is going to converge or diverge. This is very simple. Now let's talk about the last keynotes. Please pay attention to all these keynotes. They are very important. So the last keynote is that the decreasing of a function can be determined from the first derivative of the function. So if I give you a series of a of n, then if I convert it to integral of f of x dx, let's say from 1 to infinity, we are saying that if you want to prove that a series is going to be decreasing for this point where we are considering all the 3 to be active, we can do that by first finding the first derivative of the function. If we get a negative value for the first derivative, we have to say the function is decreasing. Are we okay? And from that same first derivative, it will help us to know where to start the lower limit from, whether from 5 to infinity or from 2 to infinity. We'll solve examples and we'll see how we will. So basically, these are the foundation of the integral test. Getting to know that we need 3 things to agree that we will have to use the integral test on a function should be continuous, should be positive, and should be decreasing. And the three notes that I explained is also telling us some key notes about the integral test, that is going to always tell us the divergence and convergence, but not going to give us the direct sum of the integral. Are we okay? All right. So now let's get into an example and solve using the integral test. Now example 1. Test for the convergence or divergence of the series using the integral test. So we have this series given. So our solution. So first we must write down our series. So it is summation of the series from 1 to infinity of 1 on n squared plus 1. So basically we need to establish three things to test if the series is positive, to test if it is continuous, and to test if it is what? Decreasing. All right. So the positive we are going to test. So looking at this function or expression, if from the interval chosen 1 to infinity, it should always be between the interval given from n equal to 1 to where? Infinity. If I put any value from 1 to infinity into this equation or into this expression, it is always going to come out as a positive value, right? So if I say 1 on 1 squared plus 2, 1, that is going to be a positive value. If I put in 2 here, it is going to be a positive value. If I put in 3, it is going, so it is always positive from the interval 1 to what? Infinity. All right. So now, here from the previous slide, I told you we can test for decreasing and continuous from the first derivative. But sometimes too, you can look at the equation and tell, but it is always proper to use the first derivative. But the positivity, you can use this original state to test if it is going to be positive. So now if we want to test for continuous and decreasing, now we can use the first derivative to test for that. Now let's find the first derivative of this function. Are we okay? Using the quotient rule, that means the first derivative dy on dx for this only function, that is going to be what? The formula vu prime minus, we are going to have u v prime on v squared. Here we are going to say our v is what? N squared plus 1 and our u is 1. Now putting it into the formula v, that is going to be n squared plus 1. The derivative of u is going to be 0 minus u, which is 1, and the derivative of this is going to be 2n. Everything on n squared plus 1 all square. If we simplify, this is going to 0, so that is going to be negative 2n on n squared plus 1 all square. So what do we see? That's the derivative is giving us what? A negative value. Because negative, whatever value of n you put in, this expression will always be negative. Even if the denominator is positive, since the negative is upwards, it is going to affect the equation and make it always what? Negative. It is decreasing. Are we good? Yes. Now let's talk about the continuous. It's from 1 to infinity, like this relation. Anytime I put in the value from 1 to infinity into the expression, it is going to give me that negative value. If n is equal to 1, it is going to be negative. If it is equal to 2, it is going to be negative. So from 1 to infinity, it is always what? Negative. Now it is established that this expression is positive. It is continuous with the interval given. There are some sometimes you put in from 1 to infinity and it will not be giving you negative for the derivative. So you have to now move from 2 to infinity. So wherever you end and it is continuous, you pick that interval. And we've seen that it's always going to be decreasing because the denominator is always going to be higher than the numerator, which will make it continuously decreasing. So we have established that we can use the integral test. Now that we know we can use the integral test, what do? We have to go ahead and test. How do we do that? So I'm going to say my summation of the function from n is equal to 1 to infinity of 1 on n squared plus 1 is going to be represented by a function f of x, which is going to be 1 on x squared plus 1. Are we okay? So now we are going to apply the integration, which is going to be integral from 1 to what? Infinity of x squared plus 1 dx. What is this? When you learn your integration, you know that integral from 1 to infinity is an improper integral. So we have to convert it to a proper integral. And this is how you do it. You introduce a limit such that a value, say b, approaches that same infinity. So we are going to, now this is a proper integral from 1 to b of 1 on x squared plus 1. Are you okay? Dx. Now, the integral of 1 on x squared plus 1 from the identities you can easily know is tan inverse. Integral of 1 on x squared plus 1 is always tan inverse. So we are going to say that this implies that we are having limits as b approaches infinity of tan inverse of what? X. Now the limit is from 1 to what? B. What do? We have to put in the values of what? The limits. So this is going to imply that we have limit as b approaches infinity. We put in the value of tan inverse of b minus what? Tan inverse of 1. Are we good? All right. So this is going to be, so this is the same as tan inverse of a very big number to infinity. And that is going to give us a pi on 2. In terms of degree, that is going to be 90. Are we okay? That is going to be 90, or in terms of radians, that is going to be pi on 2. Tan inverse of a very big number is approaching pi on 2. Are we okay? Minus tan inverse of 1 is going to be what? 45. Are you okay? It's going to be 45 in terms of degrees, but since we are working in radians, that is going to be what? Pi on 4. And when we solve pi on 2 minus pi on 4, we are going to get what? Pi on 4. And since this integration is giving us a definite value, that means the integration is what? Converging. It converges. So you have to conclude that since the integral test converges, the series is also what? Convergent. So this is a convergent what? Series with the integral test. So this pi on 4 is not necessarily the sum of a series from this. Summing the series you get from 1 over n squared plus 1, where n is 1 to infinity. This is not the value. Are we good? But since it is converging at a single value, then the whole function is going to what? Converge. Now let's go to our example 2 and see how best we can also solve that. Alright, so this is example 2. Now, it says test using the integral test for the convergence or divergence of the series. So we have a series given and we have to test with the integral test if it is going to converge or diverge. So straight away we are going to write down from n is 1 towards infinity of 3 on 2n minus 1. What are we supposed to establish? We have to establish if it is the expression is what? The function is positive, continuous from the interval given, and also to know if it is what? Decreasing. Alright, so now what do? We have to check from 1 to infinity. Is it going to be positive? Yes. When you put n from 1 to infinity, any value inside, it is always going to be what? Positive. We are always going to have a positive value. Very good. Even from here, you can know that when you put in the value of n to be 1 to infinity, the function is going to what? Decrease, because the denominator is going to be always increasing, causing a constant here to be what? Decreasing in the solution. But because of the way we can get a different interval, let's use the first derivative approach. So first I will find the first derivative within that. Are we okay? So now with the quotient rule, dy on dx be u prime minus uv prime on v square. So from this, our v is going to be 2n minus 1 and our u is going to be 3. So putting in the values, we are going to get 2n minus 1, which is v, derivative of u0 minus u3, and that is going to be, when you differentiate this, you are going to get what? 2, right? Okay. Everything on 2n minus 1 all square. So this will go to 0. So we are going to get negative 6 on 2n minus 1 all square. So this means that whatever value we put in for the value of n 1 to infinity, since the numerator has a negative, the answer will always what? Be negative. That means it is decreasing. The fact that we are having a negative for every answer means the function is going to what? Decrease. And also, we are still going to get the negative for every value of what? N from 1 to infinity. So, continuous is established, decreasing is what? Established. Very good. Alright. So now since we have them, let's try to solve the problem. So this means that my summation from n to 1. So in the next episode, we'll solve an example where we are going to have a change in the limits. But for now, all the limits is going to be from 1 to infinity because it says so. 2n minus 1. So representing it is going to be f of x equal to 3 on 2x minus 1. Very good. So we have to introduce our limit. So first our limit is going to be 1 to infinity 3 on 2x minus 1. But since limit 1 to infinity is improper, we are going to have to introduce our limit as a certain value b approaches infinity of 1 to b 3 on 2x minus 1 dx. Alright, so now we want to integrate this function. You can use the method of substitution where u is equal to this to solve this equation. But I also prefer to use, we know that anytime you have a derivative where f of x this way, if the numerator is a derivative of the function at the denominator, dx, then the answer is going to be ln of what? The f of x. I'm using this shortcut. So this means if I differentiate the denominator, I'm going to get what? 2, right? So that means I can introduce a 2 on 2, say limit as b approaches infinity of 3 on 2x minus 1 dx. This thing is the same as bringing these 2 inside and bringing the 3 outside. So that is going to be 3 on 2 limits b approaches infinity. This is from 1 to b. 1 to b of 2 on 2x minus 1 dx. Now we've seen that if we differentiate this, we are going to get that. So that means the answer is going to be 3 on 2 limit as b approaches infinity of what? The natural log. That means ln of what? 2x minus 1. Now with the upper limit 1 to what? b. Let's put in the value. That means we are going to have, since 3 on 2 is constant, limit as b approaches infinity. This is going to be limit of 2b minus 1 minus limit of 2 by 1 minus 1. Now, b is approaching infinity. So, limit as b approaches infinity multiplied by 2 is going to be a large value, minus 1 is going to be a large value. So, the natural log of a value approaching infinity is going to be what? Infinity. So that is going to be 3 on 2 by infinity here minus, this is going to be natural log of what? 1, and that goes to 0 minus 0. So infinity minus 0, infinity multiplying 3 on 2, that is going to give us what? Infinity. So that means according to the integration, we are getting infinity, which means it what? Diverges. So since the integration is diverging, then we can conclude that therefore the series diverge. So this is a divergent series with the integral test. Thank you for watching this episode. Please subscribe to the channel, like the video, share, and see you in the next episode for more complex examples.